Hey everyone! Ever wonder how a scratched CD can still play music? Or how a blurry QR code can still take you to a website? Or how we can receive crystal clear images from spacecraft millions of miles away? The answer is something called error-correcting codes, and it's pure mathematical magic. In the digital world, information is stored and transmitted as sequences of zeros and ones, called bits. But things can go wrong. A CD gets scratched, a QR code gets smudged, there's interference in a radio signal. These can cause errors, flipping a 0 to a 1 or vice versa. If we just sent the raw data, even a single flipped bit could corrupt the entire message. That's where error-correcting codes come in. They add redundancy to the data in a clever way, so that even if some bits get flipped, we can still recover the original information. Let's start with a super simple example, a parity check. Imagine you want to send the message 1011. We can add an extra bit, called a parity bit, at the end. We'll use even parity, which means the total number of ones in the message, including the parity bit, should be even. In 1011, we have 3 ones. To make the total number of ones even, we add a parity bit of 1. So, we send 10,111. Now, let's say one bit gets flipped during transmission, and we receive 10,011. We count the ones. There are only 2, an odd number. We know there's an error. Now, if one bit flips in a group of 3, say we receive 110, 0, 111, 111, we can use majority voting. We see that the first group has 2 ones and 1 0. We assume the majority is correct, so the original bit was probably a 1. We can do this for each group of 3 and recover the original 1011. This is a very basic example. Real-world error-correcting codes are much more sophisticated. QR codes, for example, use something called Reed-Solomon codes. Reed-Solomon codes can correct multiple errors, even if whole chunks of the code are missing. They use advanced mathematical techniques involving polynomials and finite fields. It's pretty complex, but the basic idea is still the same, adding redundancy in a clever way to allow for error recovery. CDs use a similar type of code, called cross-interleaved Reed-Solomon coding, or CIRC. This interleaving spreads the data out across the disk, so that a scratch doesn't wipe out a whole chunk of contiguous data, making it easier to correct. And in deep space communication, where signals are incredibly weak and noise is a huge problem, we use powerful codes like turbo codes and LDPC codes, low-density parity check codes. These codes get us incredibly close to the theoretical limit of how much information can be reliably transmitted over a noisy channel. So, error-correcting codes are essential for our digital world. They're the unsung heroes that protect our data from the inevitable errors that occur during storage and transmission. It's a beautiful example of how abstract mathematics can have incredibly practical and powerful applications. What other technologies do you think rely on error-correcting codes? Let me know in the comments. And if you enjoyed this dive into the magic of error correction, be sure to like and subscribe for more videos exploring the wonders of mathematics and technology. Thanks for watching.